Hi there, my name is Tuwil. I'm going to be doing a presentation on distillation pressure selection, optimum pressure. Column optimum pressure is fixed before the design equations are solved. These are mass and energy balance equations. One reason for this is that there are no fast and easy algorithms for solving the design equations for pressure. If the outcome of the design is unsatisfactory, a new pressure must be assumed and the calculation becomes iterative. So most designers, they just set the pressure in distillation columns at 1 atmosphere, despite the fact that the reflux drum temperatures are significantly greater than the 322 Kelvin or 50 degrees Celsius minimum needed to use cooling water in the condensers. If relative volatilities increase with decreasing temperature, which is often the case, the pressure should be low as possible. Hence, the pressure should be reduced till a dew point temperature or bubble point temperature of 50 degrees Celsius, even if it means the distillation column is working under vacuum conditions. So whether it's dew point temperature or bubble point temperature depends on the condition of your product. If it's a vapor, then you find the dew point temperature. Then if it's a liquid, you find the bubble point temperature. So this leaves the question for temperature approach. We normally need at least 10 to 15 degrees Celsius difference between the cooling water utility and the process condensation temperature in order to keep the size of a condenser reasonable. So this 10 to 15 degrees Celsius difference, we call it temperature approach. As an example, determine column operating pressure. Propylene is separated from 1-butene by distillation into a vapor distillate containing 90% mole propylene. Calculate the column pressure if the partial condenser exit temperature is 100 Kelvin, the lowest attainable temperature with cooling water. You see, these ones, they used 37.8, but most designers, they use 50 degrees Celsius. Determine the composition of the liquid reflux. Use the Redlich-Kwong equation of state. Let's go to our simulation environment. I'll show you how to do it. Example 1. We use the thermodynamic property package. It's a new one. Okay, we're told to use the solve Redlich-Kwong or the SRK, so we'll select that. Then our components, we have propylene. So just type propylene. We also have 1-butene. 1-butene. What is 1-butene? To configure to make sure our interaction parameters are that of the SRK. As you see, it had put penropsone, which is the default, so I change it to solve Redlich-Kwong. Okay. Yes. Okay, let's go and flash this stream and see. All right. So what are we given? We're told it's 100 Fahrenheit, 200 patient kilopascals. So we put a dummy figure of 100. And then what temperature Celsius? What was it again? 37.8. 37.8. Propylene, what's the mole fraction of propylene? It's 90%. So it's 0.9. There we go. We'll put basis of 1 moles per second. And if you go away, because it's just a basics, right? So let's flash this frame. What have we told? Into a vapor distillate. So we are looking for dew point, right? Since it's a vapor distillate, and at dew point, we have a vapor fraction of 0, almost 0. Because we have only a tiny fraction of the liquid fraction, so you can assume that the vapor fraction is 1. So we use the current temperature since we are looking for pressure. That's okay. Kilopascals, and our answer is in what? PSI, sorry. Some PSI. PSI. There you go, which is almost 186. So, which is so we're looking for PG, as I said, 800 Fahrenheit, since the distillate product is vapor. So we found that it is 186. So the opening pressure of the partial condenser outlet is that. So also we're asked to look for the vapor distillate composition. You know, is that what of the liquid, because you're giving what about the liquid reflux composition? Then we go back again to our simulation environment. We compare the vapor is what we inputted, 0.9 and 0.1. What's the liquid? 0.76, 0.23. And I took this example from separation principles by CETA, that edition, by the way. So we see here it matches 186 and also the 0.76 and 0.24. They were using hand calculation. I was using a simulation. Okay, let's go back to our presentation. I have a second example. So the NC4H bottoms product from a column is the composition given below. So we have iButane of that much, N-butane of that much, I-pentane of that much, N-pentane of that much, and our molar flow rate is to 270 kilomole per hour. So if the pressure at the bottom of the distillation column is 100 pound per square inch absolute, or 689 kilopascal, estimate the mixture temperature. So a given pressure, we are looking for temperature. And you have to know that our bottoms product is always a liquid. Therefore, we are going to look for T bubble. Let's go back to our simulation environment and build it. So since all those are now non-polar components, we're just going to use the Penrose as our thermodynamic model. You can go back to my presentation on how to select the thermodynamics model at home. You get back to the same answer of Penrose or any other equation of state thermodynamics model. So here I'll select T. I'll go to new. As I said, I'm going to use Robinson. And what do you have? iButane and N-butane. iButane, isobutane. Then I have the normal butane. N-butane, so I'll go here, change to N-butane, then put it there. Okay. Also, so pentane and normal pentane. So pentane, and pentane. We have isopentane. So pentane, there we go. Then go to configure to see what interaction parameters are there playing role this one. Okay. There's some missing interaction parameters here, but this is a simple calculation, so we should be fine. Okay, let's flash the stream. Not white. There we go. Back to our question. By the way, I took also this question from Separation Processes by CEDA, which is the 3rd edition. What is it? So I'm trying to look for the question. It's up there. Bear with me. Okay. So 0.0319. Then N-butane 7992. Then pentane 0.0648. 0.0648. Isopentane. Yes. Then we have the molar flow rate of 270 kilomole per hour. Okay, let's go. 270. And then pressure with 4 it's 100 psi. So it's 100. We want our temperature in what units? In Fahrenheit. We'll put it value of 102. Okay, let's go flash this stream. So we also know that the bottom's product is always a liquid, so we're looking for bubble point. For bubble point temperature, so our vapor is almost 0. using the current pressure. Yes, there we go. So we get the 153. And on cedar, and this is, I'll show you something. If you go to cedar, they made, is page 149, they made a big mistake because he was looking for the bubble point. So the problem is a liquid is pumpable with the following combo. So the bubble point temperature can be estimated, right? But they did not estimate the bubble point temperature. Instead, they estimated the dew point temperature. Hence, they got their temperatures T159, right? And I can prove it to you if I go here and look for instead of bubble, I look for dew point temperature, which means at dew point, we have a perfection of 1. So that's how they got this 159, but which is a mistake. So you should take a note of that. If you have any queries about that, hit me on my email address. I'll show it at the end of the presentation. So let's continue with the presentation. So limitations of the 322 Kelvin rule. For some light components, a common 322 Kelvin reflux drum temperature requires the column's pressure approaching the critical points, right? In this case, severe hydraulic problems may occur because of diminishing vapor-liquid density difference, which means the vapor and the liquid, they become the same at the critical points. Although it can usually be avoided through setting the column pressure half to the critical pressure, the resulting low condenser temperature or pressure usually requires refrigeration or mechanical vapor compression, which means your temperatures are far less below 50 degrees Celsius, and you can no longer use water as your cooling medium. For example, ethylene and ethane separation is usually conducted at 15 atmospheres and at approximately minus 40 degrees Celsius at top, inevitably requiring brine water and consequent refrigeration. The second one are those are thermally unstable components, those that decompose or coke or polymerize at elevated temperature. A maximum column bottom temperature should be constrained, which in turn dictates the condenser pressure, because there's a relationship between the rig boiler pressure and the condenser pressure, and the relationship is based on the pressure drop of the trays. Under such circumstances, vacuum operation becomes necessary. For example, ethyl benzene stirring system requires sub-ambient operation to maintain a temperature low enough to prevent stirring polymerization in the boiler. Given the distillate composition specification, the condenser temperature may be out of the cooling water range, but within that of an expensive refrigeration. So let's go back to our methanol water simulation. So remember, we set our temperature at 1 atmosphere. Then the corresponding distillate bubble or condenser temperature was found to be 65 degrees Celsius, which is still too high. You know what I mean? We can still reduce our temperature to 50 and still be able to use water. So temperature down to 50 degrees Celsius could be utilized and still use cooling water, you know. So which means if we reduce our temperature, ultimately we are also reducing our pressure. So let's find the bubble point pressure of the distillate at 50 degrees Celsius by flushing the distillate stream. So we go back to our simulation environment. Remember, we have our methanol. We'll come here. right? Remember, we only set our pressure at 1 atmosphere. That's what other designers use because they are trying to avoid to use vacuum pressures. But you see this temperature is too high, you can still reduce it to 50 and also reduce our pressure to negative values to get our optimum pressure, because this is not the optimum pressure, this is what we set. So okay, let's put 50 here. Right, then we come down here, molar vapor fraction. We want our distillate was liquid, so we're looking for bubble point. So we have just a small amount of vapor, so we'll say it's 0. Then we'll use the current temperature to get this corresponding bubble point pressure, so which is 0.54, right? Then we come, that's so my mistake here, I put so it's 0.54. 54. So hence we found that the optimum pressure is now in the vacuum is less than 1 atmosphere. Hence the optimum pressure obtained by lowering the pressure to the point we can still use cooling water is 0.54 atmospheres. Hence a vacuum system is required. Right. So we go back and change this. Our pressure is now our pressure is no longer 1 atmosphere. So I'll go to units and change pressure atmospheres. So it's 0.54. Also, we're using the optimum pressure. This is the optimum pressure. Okay. You wait for it to solve, and boom, there you go. Back to our presentation. So now we have our optimum pressure is 0.54. So the other rationale to use is to choose pressure with minimum boiler energy requirement to lower operational costs. And I'll do a presentation on this on my later presentations. And thank you very much for watching. If you have any queries or questions, please contact me on tubasbond@gmail.com. Please like, subscribe, and comment on my YouTube channel. Also, click the link on the description to support my t-shirt sales business. I'll see you on the next presentation. Bye.